Hey guys, this is Johnny, and in this tutorial I'm going to create a basic third-person controller using Godot 4. You may have come across my previous series, which was created using Godot 3. With the major changes in Godot 4, a lot of you have been asking to update the demo to the latest version. But I decided to create it from the ground up with a bit more cleaner approach with some scalability in mind. So without further ado, let's get started. So here's an overview of this demo. The player will have these three components that will have their own responsibilities, which you can already tell by their names. The player will have these four movement states: stand, walk, run, and sprint, which will be instances of this class so that they can have their own properties. The player class will take the user input and set the current movement state accordingly. Then it will pass the state to each of the controllers and they will take the values to do their own work. The movement controller will take the movement speed and acceleration of each state and set the player velocity accordingly. The animation controller will take the ID and animation speed data of each state and change the player animation. And the camera controller will take the camera FOV data to change the field of view. In Godot, I've created a simple environment with CSG Box 3D and enabled the use collision so they essentially become static bodies. In the material, I've added a simple square texture as albedo, and under UV1, I've enabled the triplanar and world triplanar so the texture repeats, having its own position globally locked. I've created this character with some animations in Blender, and I'm going to simply export the GLTF of this model inside the project directory. If the GLTF exporter is not available in your Blender, you can go to Edit, Preferences, Add-ons, Search GLTF, and simply enable it from here. In Godot, I'm going to right click on this model, create a new inherited scene, and then I'm going to save it as is. In the main scene, I'm going to add a new character body 3D node and I'll name it player. I'm going to add a collision shape 3D, define the shape, then I'm going to add a node 3D, name it mesh root, and drag the player mesh here. To create a third-person camera, I'm going to add a node 3D, which will be the root of the camera. I'll add a child node 3D, which will handle the yaw or the horizontal rotation of the camera, and another child node 3D of that, which will handle the pitch, which means the vertical rotation. I'm going to add the camera as a child of this, and in the code, I'll modify the horizontal rotation of this node and the vertical rotation of this node. I'm going to create a new script called camera controller and attach it on the cam root node. Here I'm going to create all the necessary variables. In the input function, whenever mouse motion is detected, the yaw value is modified according to the x value of the event relative. The event relative is basically the mouse movement relative to the last frame. I'll multiply it with the sensitivity variable to have more control. I'm going to do the same thing with the pitch, but this time taking the y value of the event relative. In the physics process, I'm going to lerp the y-axis rotation of the yaw node and the x-axis rotation of the pitch node towards the respective target values. In Godot, rotation means the local rotations of the nodes. If we use global rotation, it won't work the way we want. And if I play this, you can already see some results. To remove the mouse from the screen, in the ready function, I'll set the mouse mode captured so the game captures the mouse when I run it. To prevent the vertical rotation from going too far, I'm going to add two variables, max and min, and clamp the pitch value so it doesn't cross the limit. If you don't want a smooth camera, you can also set the values directly. To prevent the camera from going inside the walls, I'm going to add a spring arm 3D and make it the parent of the camera. The spring length defines how far the camera will be. If I play this, you can see we're almost there, but the camera is still getting inside the wall a bit. I'm going to add a sphere shape 3D with a small radius so the camera doesn't get inside, but you can see it's still a bit jittery. After a lot of experimentation, I've found that using the Jolt physics engine solves this problem. To get Jolt, go to AssetLib, search Jolt, download and install. And then go to Project Settings, Physics, 3D, press Advanced Settings, then change the physics engine to Jolt and restart the project. With the Jolt physics engine, the spring arm collision becomes much smoother. Here's a comparison of the default and Jolt physics. If you're liking this video, you can subscribe so you don't miss my future videos. And you can also join my Patreon page to support my content. Before we move to the player movement, I'm going to create a simple state system. I'll create a script called movement state, make it extend resource, and then set the class name as movement state. I'll also add the necessary variables I discussed earlier. So now I can right click and create a new resource, search for movement state, and create a resource object of this type. I'll duplicate and rename them as stand, walk, run, and sprint. I'll double click and set the data for each of the resources. So each resource is the movement state that has its own set of data. I'll add a new script to the player that has an exported dictionary called movement states. In the inspector, I'm going to manually add key value pairs by making a key string and making the value an object. I can then set the string and drag the resource object. I'll do this for all the movement states. I'll use this signal called setMovementState to pass the movement state as an argument, which I'm going to emit in the ready function to initially set the movement state as stand. In project settings, input map, I'm going to add all the necessary actions for now. In the script, I'm going to create a variable called movement direction, and in the input function, I'll modify its x value with the action strength left subtracted by right. I'll do the same for the z value with forward and back. Whenever an action is pressed, its strength becomes 1. So this is a simpler way to define the direction vector. Also, pressing the counter directional buttons cancel each other out. With this, I'm going to determine if there is movement, and if there is, here I'm going to emit the signal and pass the movement states according to the user input. In the physics process, I'm going to send the movement direction with this signal whenever movement starts. I'm sending this in the physics process because I'm going to need to update the direction in every frame for the movement controller. Also in the input map, I've created a movement action and bound all the movement keys to this action, so these lines only run when the user interacts with the movement keys. This way I can make sure the signal is not getting fired unnecessarily, which can cause performance issues if any functions connected to it have some costly calculations. I'm going to add a new node, call it movement controller, and attach a new script to it. Here we need a reference to the player and mesh root and some necessary variables. I'm going to attach the player node and the mesh root node here. Referencing like this can make sure the code base stays a bit modular and can open up some opportunities to reuse the code somewhere else. I'll create some functions that receive the movement states and the movement direction from the player. As we discussed earlier, I'm going to take the speed and acceleration values from the movement state. This way, each state applies their own movement speed and acceleration values to the movement controller. I'll connect the signal from the player script with this function using the pick button and with this button unchecked. I'm also going to connect this function with the set movement direction signal from the player script. Here I'm going to set the movement direction received from the player. In the physics process, I'm going to set the velocity x and z values like this. I'm taking the normalized values of the direction vector so the length of the vector is always 1. I'm ignoring the y value because we would need it later for creating jump mechanics. Here I'm going to lerp the player velocity and call movement slide, and I'm also going to rotate the mesh root node towards the movement direction here. I'm subtracting the player rotation here in case you want to rotate the player root body in the editor while designing levels. Otherwise, you can ignore this one. As you can see, the player is now moving according to the input, but the movement is not getting modified with the camera direction. To fix that, I'll add a signal in the camera controller script called setCamRotation that takes a float argument, and then I'll send the rotation of the yaw node here. I'll connect the signal with this function that says the camRotation variable. And here I'm going to rotate the direction along the vector 3 up axis using the camRotation. So now the player model looks towards the movement direction. In the camera controller script, I'll add this function which takes a movement state as an argument. Here I'm going to create a twin variable, and here I'll create a new twin and animate the FOV property of the camera node according to the camera FOV variable of the movement state received as an argument. I'm also going to set the transition and ease to make the animation look smoother. I'll also add these two lines so if the function gets called multiple times, the previous twin gets killed. This way we can avoid any unnecessary overhead. I've put some values for the camera FOV variables in all the movement states, and you can see here the field of view changes with the movement. To create the animation system, I'm going to add an animation tree node under the mesh root node. I'll make the mesh object editable so the animation player is visible, which I'm going to attach to the animation tree. As a tree root, I'll create a new animation node blend tree. Here I'm going to create a blend space 1D and a timescale node to modify the animation speed. In the blend space editor, I'll make the lowest value 0 and the highest value 3. I'll also set the snapping value to 1. I'm going to add stand, walk, run, and sprint on the 0, 1, 2, and 3 positions. Then I'll create a new node called animation controller and attach a new script. Here I'm referencing the animation tree and the player, which I'll have to attach manually. I'm going to create a twin here and create this function which will be connected with the set movement state signal from the player script. Here I'm destroying the previous twin again, and here I'm going to call the twin property function to animate the blend position and the time scale properties of the animation tree. I'll use parallel here so they both run simultaneously. If you select the animation tree, you can simply drag and drop the parameters into the script. The movement states have IDs 0, 1, 2 and 3, which can be mapped with the animation I've placed in the blend space earlier. I'm also taking the animation speed from the movement state, where each state has its own animation speed. So if I run this, you can see the animations are working for the respective movement states.